the cord a few times.
Is that why it's all steel? So
That's right. Yep, it's made of tough materials so that Mr. Everly cannot damage it easily. Okay, so last year, we learned all about projectile motion, and really there were two kinds of problems we looked at. One where the velocity was horizontal and it shot off the table and hit the floor, and then one where the velocity was set at an angle, and we watched the big, beautiful parabola and we solved those equations. Now, if you go back, and I actually had this set up here for yesterday and didn't get quite to it, so hang on just a second. You might remember these graphics from last year, and this will make life a lot simpler if you remember these graphics. I've got a ball that I'm just dropping, and when I drop it, we take a picture every 1/10 of a second. If I take a picture every 1/10 of a second, you notice the first 1/10 of a second doesn't go very far. The second 1/10 of a second, it goes a little further, then a little further, then a little further, then a little further. So it's showing how this thing's accelerating toward the Earth. If I roll it across the table and it rolls to the edge of the table, while it's on the table, it'll maintain a constant velocity, roll, 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 because there's no unbalanced forces on it. Okay? Gravity is being canceled out by the force of the table up. We'll get to that later, so don't worry if that doesn't make too much sense. You get to the edge of the table, and let's say I turn off gravity just at that point. This ball on the x-axis is maintaining a constant velocity. So, when you put it all together, you get this beautiful parabolic path that rolls off the table and goes down the red path here and hits the floor. Okay? So, my mantra last year. Yes, sir?
If you were to roll a ball off the table in like zero gravity, once it leaves the edge of the table, would it keep spinning still? Or?
Well, in zero gravity, we'd have a hard time getting it to stay on the table. So rolling it in zero. So my example is always, I roll it across, and then just at the edge of the table, I hit the gravity switch, and it keeps going. But to answer your other question, yes, it would have rotation. We're not worried about the rotation right now, and it won't affect the projectile motion. In theory, it could affect the projectile motion because enough spin creates something called the Magnus effect, which is why you can throw a curveball. You put enough spin on it, and you get some interesting paths through the air. But we're going to ignore air resistance as well for now. We're going to throw it in later. Remember, education is a series of decreasing lines. So I'll show you how it works without air resistance, and then, we slowly add the layers of complexity. All right, remember the moral to this story was, if I fire a bullet horizontally, and at the same time I pull the trigger, I let go of a second object, say another bullet that's not in the gun, I just let go from the same height, the two bullets will hit the ground at the same time. And Mythbusters did it, and it worked. It's really crazy. I have a demonstration you saw last year with the ball bearings. You shoot them across, and you shoot one sideways, and you just let one drop and hit the ground at the same time. So it's bizarre but true. It goes boom. So you fire a bullet from this height. That's how long it takes for it to hit the ground. It's like, all right. I have students who fight me on that like all year. They're like, no, it's not true. So yes, it is. No, it's not true. Yes, it is.
I've got another question.
What do you want, Buck?
So, like, they put rifling in rifles to make the bullet spin, right?
Yes.
So is the spinning bullet not heavy enough to create that Magnus effect, or?
Now, the Magnus effect occurs for a spin that is like perpendicular to the ground. Then I'd have a nice curvature this way. If I've got a spin this way, then I would have a curvature up or down. Okay? What you also need is some surface texture. So the bullet doesn't have a whole lot of surface texture. So there's not a whole lot of Magnus effect. So you see these movies, you know, where they try to curve the bullet and all, it's all BS. Okay. Yeah. The only reason for the spin on the bullet is to stabilize it. So it gives it gyroscopic stability so that the point is cutting through the air. If the bullet tumbles, it'll go much less, I should say, not a lot, much less distance because of air resistance. So the spin is actually a little trick to keep air resistance down. Okay. Next. There we go. We also had this situation where if I take a ball and throw it up in the air, it goes fast initially. Remember, these pictures are 1/10 of a second apart. So it goes fast, slows down, slows down, slows down, slows down, slows down, stops, then speeds up, speeds up, speeds up back on the way down. Also, if I do this, I'm giving it a little sideways oomph. But gravity's not acting on it sideways. It's got a constant velocity sideways. So when I put those two motions together, I get the big, beautiful parabolic path. So my mantra from last year is constant velocity on the x, constant acceleration on the y. Object moves with a constant velocity on the x, constant acceleration on the y. And do you remember what happens if you're driving your pickup truck with a cannon in the bed of the truck that's pointing straight up, and you fire the cannonball while you're driving down the road? Where does the cannonball end up? Yeah, back right into the back of the truck, right? We saw that video of the kids playing car bowling, and they took out their back window. Okay? Also, I've got this demonstration. Oh, I put it away. I can't believe I did that last night. I'm sorry. Be right back. Mr. Everly was bad. Because we did it during 0 hour yesterday.
I thought you had to stop.
It's really cold. It's like freezing these days.
That is like a sweatshirt.
Okay, remember this thing?
They do a lot, but they consider it a jacket, so they will.
Very good.
If you got a cannon on a car and you fire it straight up, you know, I put it away last night without thinking. It's important to think when you do things.
Yes.
Let's see if it still works.
That's one thing.
Okay, so I've got a cannon inside this cart. I know it's active because the little light's blinking. Now it's a little yellow ball. Okay, set up the cannon. When I run it past that post will send a little piece of metal through this photo gate and fire the ball. Oh, it bounced out, but you see what's going on. Might be a little bit off kilter here. Let's do it again. Ooh, it got out of alignment. But you can see it comes back and hits the car. So it's not a good idea to be driving your pickup truck with a cannon in the back that's pointing straight up, because the cannonball will come back down and hit the car. Okay. What'd you say? Yeah, there's a little alignment problem here, a side-to-side alignment. I think I might have hit it or something when I. Oh, I'm sorry. I really don't care what you believe.
It's not going fast enough.
It's hitting the edge. Make it go faster?
Yeah.
Okay. There it goes.
Yes.
Now you believe. Okay.
See, you want too slow.
I'm sorry. Sheesh. All kinds of complaints. All right. So I can lose this from last year. We'll come back here. Okay, we're going to try the pen of death here. A little blinky light tells me it's connected. Oh, I hate this thing. Okay, so this thing rolls to the edge and does, well, okay? And again, if we take a look at it at different points in its flight, we would say to ourselves, look, in the x direction, the velocity stays exactly the same every single time. The y direction, the velocity starts out at 0 over here, but gets bigger and bigger and bigger because it's accelerating downward at 9.8 meters per second squared. With this guy, if we take a look at the ball at different positions, we'd say, okay, it starts off with this initial velocity in the y, this in the x. The x never changes. It's constant. The y starts out big, gets smaller and smaller, goes to 0, then gets bigger and bigger and bigger again. Okay? So there's all kinds of changes in velocity happening in the y, no changes in velocity happening in the x. So that's the thing to keep in mind as you solve these problems. All right. Check this out. Whammo, whammo, whammo. Okay. So here's an example that we could have done last year. It says a diver runs off a 30-meter cliff with a horizontal initial velocity of 5 meters per second. How far from the base of the cliff does he hit the water? At what angle does he hit the water? Part B we probably didn't do last year, but part A we did. So, whoops. Let's see. Can I back up? Oh, I sure can. I got to hit this. Okay. So, here's our diagram. This diver is running to beat the band in that direction. He runs out of cliff, or runs out of ground and falls off the cliff and goes, well, splash. Okay, the initial velocity of the diver, 5 meters per second. 30 meters is the height of the cliff. Okay. Now, we could set this up with I hat, J hat, and it would work out beautifully. But quite often what we have to do is intermingle the I hat and J hat in order to make this work. The thing that stays the same for the x and y axis is delta t. Time is the same. Doesn't matter if you're traveling on the x or the y axis or you're just looking at his x velocity or his y velocity. Delta t is the link between the two. So what we did last year, and this technique works really well, is to draw the big T and say, this is going to be the delta x side, this is going to be the delta y side. So we'll do all our x component calculations, all our I hats on the left, and all our j hats or y component calculations on the right. The equation that 70% of the time works for these problems is the Dragon equation. Delta x equals v naught delta t plus 1/2 a delta t squared, because we're looking at distances that objects travel during an acceleration. And I want to know, what am I after? I'm after this distance right here. What would we call that? Delta x. And by the way, they give us this 30 meters. What's that? Delta y. It's almost delta y. It's negative. Yes, sir. Leave my negative sign in there. It's negative for the diver because this is his origin. This is where he's starting. So he ends up dropping 30 meters. So we have to make the delta y negative. It's a negative vector, points down. Okay, so we've got this Dragon equation here that works either on the x or the y, but I'm going to modify it for x and y. In other words, in the x direction, when he launches, does he have an initial velocity in the x direction? Sure does. So I need that first term, v naught delta t. As he flies through the air, does he have an acceleration in the x direction? Bree? No way. So there's the equation, because if I stick a 0 in for a in the equation up here, this whole term's going to die off. So all I need is delta x is v naught delta t. Delta y. When you're looking at the equation for delta y, I'm going to take this delta x up here in the dragon equation and call it delta y. Is there initial velocity in the y direction? No. It's all x. So let that term go. Is there an acceleration in the y direction initially? Oh yeah, it's negative g. So I'm going to take the dragon equation above and call it delta y equals minus 1/2 g delta t squared. This thing catches up to me sooner or later. Alrighty. So I've kind of set things up. Now I have to ask myself the question, what are we trying to find again?
How far from the base of the cliff is?
Yeah, I'm after delta x, yeah? To get delta x, I need two things. The initial velocity in the x direction, got it, 5 meters per second. I need the time he's in the air, don't got it. When that happens, walk over to the other side. Delta y, hey, I know that. G, I know that. Delta t, I can find it now. So if I rearrange this puppy, I've got delta t equals the square root of negative 2 delta y over g. So it's negative 2 times a negative 30 meters of drop divided by 9.80 meters per second squared. And I have the time this thing is in the air. Stay. So 60 over 9.8, take the square root. Okay. Anyone punching that out? I think I got the wrong answer. Hang on. 60 over 9.8. Ah, that's better. I just hit the wrong button somewhere. So we're getting like 2.5 seconds. 2.47 seconds. Now, does it make sense that the right side, the delta y part, is telling us how long it takes to fly through the air? Because remember the bullet in the gun? It didn't matter how fast we were shooting it to the side. What determined how long it spent in the air was how high above the ground. So it's how high above the ground and the acceleration due to gravity. That's all that matters as far as delta t. So we come back to our other equation and say, aha, now we've got it cooking. We've got a 5 meter per second x velocity. And he maintains that 5 meters per second for a little under 2.5 seconds. And life is very good. So the answer is like 12 meters. So 1 meter more than the length of this room. So that's quite a ways out. But it's a 30-meter cliff, so he's got plenty of time.
I read that as driver first, like he's driving the car. That was very.
Oh, that it's a driver instead of a diver?
Yeah,
Yeah, you know.
that could hurt.
Yes, it could. All right.
Make sure your windows are open so you can get out.
That's right. Make sure if you drive your car off a cliff, the windows are open.
Yep. Otherwise you're stuck.
I see. All right. At what angle does he hit the water? Now, whenever they ask a question like,
Find that kid.
we can find that. Whenever they ask a question like, what direction is somebody moving? Are you going to look at the direction of their displacement vector, their velocity vector, or their acceleration vector? When they say, what direction is that object moving? Which of those vectors would you look at for a direction? The velocity vector. So if somebody says, and tattoo this to your brain because this comes up a lot. If you have a displacement that way, that's not necessarily the direction you're moving. I mean, when you have a displacement like from here to here, you could have done this, right? You could take any path you want. So if you know the direction of the displacement vector, you do not know the direction he's moving. But if you know the direction of its instantaneous velocity at any point, that's tangent to the curve, right? It's telling us the direction he is actually moving at that point. So we need to know the direction of his velocity right here when he hits the water. Okay? So at impact, does he have a velocity in the x direction? Yeah, that never changed, right? So let me draw that in. So I know it's 5 meters per second. Does he have a velocity in the y direction? Yeah. So check it out. If I knew how fast he was going in the x, which I do, and I knew how fast he was going in the y, I could do a little inverse tangent action and figure out, okay, that direction is a little off. It's got to be tangent to that path. But you see where I'm going with this? If I could find those two components, bam, inverse tangent, I've got the angle. Okay, so the big question here is how fast is he moving in the y direction when he hits the water? Okay, 9.8 says acceleration when he hits the water. I'd like to know how fast he's moving. So how can I use the 9.8 to solve the problem, Bree? Times it by 30 meters?
Yeah.
No? Okay. So if you take an acceleration, you multiply by a distance. What are the units on that 9.8? You told me 9.8. What are the units?
Meters per second.
Okay. So the acceleration of this guy is negative 9.80 meters per second per second. We always say meters per second squared because, you know, it's nice and compact. But what we're saying is his speed's going to increase by 9.8 meters per second for every second he's falling. How many seconds is he falling? 2.47. So we can figure it out using the 9.8. You were right. But we don't want to use the displacement. We want to use the time. Okay, here's a nice little equation. Okay, remember this dude? So we could say, look, initial velocity in the y direction. If you want, you can put little y's here. Initial velocity in the y direction is 0. Acceleration in the y direction, negative 9.80 meters per second squared. Time, 2.47 seconds. Okay, 9.8 times 2.47. Answer, 24 meters per second. Oh my gosh, that's huge. All right. Okay, so down here, 24 meters per second. Can you find the angle now? What you gonna do? Find theta. You got it, inverse tangent. So I'm going to say theta is the inverse tan of 24 over 5. So we could calculate that angle pretty quickly. So that's why my diagram was a little off. That downward component of its velocity is gigantic, which kind of makes sense.
Are we not assuming water resistance either?
Well, water resistance isn't coming into play yet. This is the speed. I beg your pardon. This is the direction he's traveling when he hits the water. Of course, hitting the water is going to change the direction of travel because suddenly his y component is going to be way different. His x component is going to be way different. But we're looking at the moment of impact.
That's gonna hurt.
Great question. It will hurt depending on how he hits, right? but you're right. That's pretty fast. Water is pretty hard when you hit it at that speed. All right. So I'm getting, I flipped it. Here I was talking to Buck here while I'm calculating, and I flipped it. It's all Buck's fault. It's not the fact that I can't use a calculator. There we go. Now I've got it. Looks like 78 degrees. Okay, so the answer is 78 degrees. How do you want to describe that? We can't say like south of east or anything because this is up and down, left, right. We can't use cardinal directions. So you'd say 78 degrees
Into the water.
below the water line or into the water. A lot of times they say 78 degrees below the horizontal.
Oh.
So that's horizontal, 78 below horizontal, we're in the water. Okay, so part A is kind of like last year. Part B, not so much last year, right? We might have touched on it, but didn't do a whole lot with it. Okay, any questions? We kind of beat that one to death, but kind of an important one. Come on. There it goes. All right. I got to move this a little bit. Sorry, Amanda. Now it's legible. Okay. A ball is thrown at 14.1 meters per second at 45 degrees above the horizontal. Someone located 30 meters away from the thrower along the line of the path starts to run just as the ball is thrown. How fast and in what direction must the person run in order to catch the ball at the same level? Okay, instant translation. I'm over here with the ball. Bree is over there somewhere, and I throw it. Now, if she's over by the first lab station and the ball does this path, that means she's going to have to start running and probably dive to catch it. Okay, sacrifice her body. All right. The question is, how fast is she going to have to run? Okay, it's 30 meters from her to me. Okay, it doesn't look like 30 meters, but it is. So how are we going to solve this problem? There's a little twist here, isn't there? What do we need to know in order to figure out how fast she has to run?
The distance that the ball's going to go.
Yeah, where does the ball land? Yeah. So if the ball goes like 10 meters and she's 30 away, she's going to have to hustle 20 meters in the time the ball's in the air in order to get here. So we need to know where the ball is going to land before we can even figure out what she has to do. Maybe it's going to go over her head and she's going to have to run the other way, right? We don't know. So our first job is, where's the ball going to land? Okay, so let me switch to drawing mode again. This thing blinks and does all kinds of stupid stuff. Okay, so here's our ball. We toss it at 45 degrees. I'll draw in the components right away. Here's our V naught, and the ball goes, lands right there. Okay, 14.1, 45 degrees. Okay. Our first job is to figure out what's delta x. Okay, as we discovered last year, the problem here is we've got initial velocities on both the x and the y. So initial velocity in the x, v naught cosine theta. On the y, v naught sine theta. Okay, so I'm going to push this up, give me a little room. We're going to do the same trick. We've got a delta x side and a delta y side, and we're going to set up the equations so it works.
We have 2 minutes.
You're right. We end at 49. I was thinking we ended at 51. All right. So delta x equals v naught delta t plus 1/2 a delta t squared is again our friend. but we have to modify it so it now works for this situation. Delta x. Is there a velocity in the x direction initially? It's called v naught cosine theta. So I'm going to change this v naught here to v naught cosine theta, delta t. Is there an acceleration in the x direction while this thing's in the air? And the entire congregation says, no. Not amen. No, because there's no acceleration that way, right? So there's our equation. Looks almost the same as before, except it's got that cosine theta in it, because our initial velocity in the x is just this piece of v naught. Other side. Take the same equation. Now I'm going to call it the delta y equation. Is there initial velocity in the y direction? Oh gosh, this is going to be hard. Okay, so keep reading the textbook. We'll continue the examples tomorrow. No assignment, because tomorrow's 0 hour, right? So we're going to attack this for a while tomorrow. We'll do some problems, and all will be good. Make sure you're doing the work, folks. This is AP Physics, so when I come around, I should not hear, oh, I didn't have time. Okay, this is a huge commitment, so for both of us. Please do get them done. And most of you are getting there, so thank you. Sir?
Question about the graph I was making for the lab.
Oh, okay.
I didn't have it on.
All righty.